Assalamu alaikum. This is lecture 11 of data security and encryption, and in this lecture we are going to continue the topic of finite fields. As discussed earlier, finite fields have become increasingly important in cryptography, and a number of cryptographic algorithms rely heavily on the properties of finite fields. And most of the algorithms involved in advanced encryption standard AES involve the implementation of finite fields. So let's have a look at the lecture contents. In this lecture we are going to discuss some mathematical properties about polynomial arithmetic, and in this topic we are going to study three different aspects of polynomial arithmetic known as ordinary polynomial arithmetic, polynomial arithmetic with coefficient in the set Z, and finding the greatest common divisor. And then we will move to the finite fields of the form GF2 raised to power n. And in this topic we are going to discuss the modular polynomial arithmetic, and we will find a way to find out the multiplicative inverse of a number. And similarly, some computational considerations will be discussed along with the concept of using a generator to generate a set or polynomial expressions. So a more important class of finite fields for cryptography comprises those with the 2 raised to power n elements depicted in the field in the form of G, F, 2 raised to power n. So these are used in a wide variety of cryptographic algorithms. However, before discussing these fields, we need to analyze the topic of polynomial arithmetic. So you must be familiar with the concept of polynomials. However, to use the concept of polynomials in the finite field, we must introduce the interesting subject of polynomial arithmetic. We are concerned with the polynomials in a single variable x, and we can distinguish these three classes of polynomials arithmetic based on the variable x. So one class related to the polynomials is when the x is treated as a variable and evaluated for the particular value of x. For example, if you have a polynomial of f of x and you are specified with the value of x, you treat this kind of polynomials to find out the value of your whole polynomial using that value of x. On the other hand, if x is treated as indeterminate, there are three possible classes. Number one is ordinary polynomial. This arithmetic uses the basic rules of algebra. Number two is arithmetic on coefficient performed by modulo p, and these types of polynomials arithmetic are the arithmetic on the coefficients of modulo p, that is the coefficient in the form of g of f p as discussed in the last lecture. The third form referred as polynomial arithmetic, in which coefficient of gf of p and the polynomials are defined modulo a polynomial m of x, and then whose highest power is some integer n. So we will briefly discuss these two types shortly, and then we will move our focus to the third type. This diagram shows the addition, subtraction, multiplication, and division of typical polynomial equations. So this is represented as ordinary polynomial arithmetic. So you must be very familiar with the definition of polynomial. A polynomial of a degree n, integer n is greater than 0, is an expression in the form of a variable or more than one variable, such as x cube plus x2 plus x square plus x2, etc., or some other equation such as this x cube plus x square. Similar equation is here, and the other equation is used is x square minus x plus x. So this form is usually represented as sigma I from 0 to n, and you have a coefficient named as a, and you have a variable named as x. So a comes from the coefficient set and the x is a variable in the question. So polynomial arithmetic includes the operations of addition, subtraction, and multiplication for the basic operations. The operations are defined in a natural way. So it is defined as the variable x was the element of the set we are going to use in our uh, finite field. However, division is similarly defined but requires that our set must be a field. That means you can perform these operations on any set that is not a field. Even if you can perform these operations on a ring, but if you want to perform the division, you must have the set that must correspond to properties of a field. So again, examples of fields include the real numbers, rational numbers, and the set Z defined for a P number prime. So you can note that all the set of integer is not a field and does not support the polynomial division. So as an example, you can take the addition. For example, if we have two equations, the first is referred as f of x and the second is referred as g of x. So f of x plus g of x is defined, and then you have a subtraction operation that is also defined, f of x minus g of x, and then you have a multiplication operation which is also defined, f of x plus g of x. So leave the division for the moment and we will come back to this in the next slides. So now consider the polynomials in which coefficients of the elements of some field f. So we refer these polynomials over the field f. So in case it is easy to show that set of such polynomial is a ring referred as polynomial ring. So here are some very useful properties to learn about. So if each distinct polynomial is considered to be an element of the set, then the set is a ring. So that means if you define any equation that is part of a set, then the set is a ring. On the other hand, when polynomial arithmetic is performed on polynomials over a field, then division is possible. So in first case, division is possible, but whole division is not possible. So this does not mean that the exact division is possible. So take a moment to clarify this distinction. So when you use a field given two elements, say A and B, the quotient A or B, A divided by B, is also the element of the field F. On the other hand, if you use the ring or your equations belong from the ring that is not a field, in general, division will result in a quotient and a remainder that will be not an exact division. So consider a division of numbers a divided by b, such as you can take 5 for a and you can take 3 for B. So if you have taken these numbers from a set S, and if the set is a rational numbers which is a field, then the result is simply expressed as 5 by 3, and that 5 by 3 will be part of that field, and it must be also the element of that set S. Now suppose that S is a field of Z7. So in this case, if we use the arithmetic operation of modulo 7 uh, to perform the division, so we get the number 5 by 3, which is translated into 5 multiplied by 3 inverse mod 7. So if we remember the table from the last lecture, that the 3 inverse uh, or multiplicative inverse of 3 is equal to 5. So we get the equation 5 multiplied by 5 mod 7, and we get the remainder 4. So which is an exact solution? Finally, suppose, because 4 actually exists in the field. So finally, suppose that the S is a set of integer which is a ring but not a field. Then 5 divided by 3 produces a quotient and a remainder of 2. So let's do the other way. So what are the possible answers? So in this case we can get 5 by 3 is equal to 1 plus 2 by 3, or in other words we can get 5 is equal to 1 multiplied by 3 plus 2. Now in this case the set is the set of integers, so this number cannot be part of the set. Therefore the division is not exact over the set of integers. Now if we attempt to perform the polynomials division over a coefficient set that is not a field, we find the division is not always defined. So even if the coefficient set is a field, polynomial division is not necessarily exact. So with this understanding that the remainders are allowed, we can say that the polynomial division is possible if the coefficient set is field, but not necessarily exact. So for example, considering this case, if we have a equation 5x squared divided by 3x. So if our coefficient set is the set of integers, so this does not have a solution because it will require a coefficient with the value of 5 by 3, which is not a integer, and it will not be in the coefficient set. So suppose that we perform the same polynomial division using our set Z7, and in this case we use the remainder modulus way of modulo 7. In this way we can produce the same result we produce in the 5 by 3 case, and we are given with the result of 4x, which is a valid polynomial over the Z7. However, as we demonstrate presently, even if the coefficient set is a field, polynomial division is not necessarily exact. So in general, division will produce a quotient and a remainder. So here are some interesting properties about the polynomial division. So given any polynomial f of x of degree n and g of x of degree m. So In this case, we specify that the degree of f of x should be greater than or equal to degree of g of x. So if we divide f of x by g of x, we get a quotient named as q of x, and uh, then we get a remainder called r of x. So this must be a number, uh, the second equation, or a polynomial. So r of x can also be defined as f of x divided by g of x and the remainder, so which can be written by f of x mod g of x. So if there is no remainder, we can say that g of x completely divides f of x. Written as g of x divides f of x, we can say that g of x is a factor of f of x, or g of x is a divisor of f of x. So a polynomial f of x over a field f is called irreducible if and only if f of x cannot be expressed as a product of two polynomials, such as in this case, if you have such equation which cannot be represented in such a way, so this kind of polynomial is called irreducible. That means you cannot factorize it and cannot reduce its degree. So both over f and both degree lower than the f of x. So an irreducible polynomial is called a prime polynomial. So we can extend the analogy between the polynomial arithmetic over a field and the integer arithmetic by defining the greatest common divisor as follows. So the polynomial c of x is said to be the greatest common divisor of a of x and b of x if the following conditions are true. What are those conditions? If the equation or polynomial c of x divides both a of x and b of x, or any divisor of b of x, a of x, b of x is also divisor of c of x. So which leads to the similar definition that we discussed in the lecture number 4 about finding the greatest common divisor. So GCD of a of x, b of x is the polynomial of maximum degree that divides both a of x and b of x. So in this way, the Euclidean algorithm can be extended to find the greatest common divisor of two polynomials whose coefficients are elements of a field. So the equality can be referred as greatest common divisor of a of x, b of x, similar to the numbers we had in the previous lecture, such as greatest common divisor of a comma b. Now we have a of x and b of x, which was equivalent to the greatest common divisor of b of x comma a of x mod b of x. So at each division or iteration, you can replace the value of b is equal to a and a is equal to remainder, such as in this case. So in the last lecture, we mentioned that the order of finite field must be of the form p raised to power n, where p is a prime and n is a positive integer. So practically all encryption algorithms, both symmetric and asymmetric, involve arithmetic operations on integers. So if one of the operations that is used in the algorithm is division, then we need to work the arithmetic defined over a field. So for division, it is necessary to have a field. So we would also like to work with the integers that fit exactly into a given number of bits with no bits wasted. That is, we wish to work with the integers in the range from 0 to 2 raised to power n minus 1. For example, if we have n is equal to 3 here, we must be able to use the number 0 to 7, and each number must be n bit wide. For example, n is 3 here and each number must be 3 bit wide. So suppose we wish to define the conventional encryption algorithm that operates on the data of 8 bits at a time, and we wish to perform division. So with 8 bits we can represent the integers in the range from 0 to 255. However, depending the set is 256 values. In that case, 256 is not a prime number, so that arithmetic performed in Z256, referred as arithmetic modulo 256. This set the set of integers will not be a field because this is not a prime number and it involves a division. So the closest prime number less than 256 is 251. So thus the set of numbers contained Z251 using arithmetic modulo 251 is a field. So however, in that case, the 8-bit pattern represents the integer 251 to 255 would not be used. So it will result in inefficient use of storage. So on the other hand, suppose we wish to use the 3-bit blocks in our encryption algorithm and use only the operation of addition and multiplication. The arithmetic modulo 8 is well defined. So as shown in this table, there are finite fields of the form GF 2 raised to power n. So there is a particular finite field of order 2 raised to power 3 that is equal to 8. So in this case, the number of occurrences of non-zero integers is uniform for the multiplication. So if you compare this table with the previous lectures table of arithmetic modulo 8 or 7, you can see the difference of numbers occurrences. So in the last table, for example, if you take the number 1, the number 1 occurred for about 4 times, but if you take this table, each number is occurring about 7 times, ranging from 1 to 7. Only 0 is occurring more than 7 times. So this leads to some useful observations. Number 1 is the addition and the multiplication tables are symmetric about the main diagonal in conformance to the commutative property of addition and multiplication. Also, all the non-zero elements defined in this table have a multiplicative inverse, which was not present in the table defined in the last lecture. If you compare this modulo 8 table with the last lecture's modulo 8 table. Also, the scheme defined here satisfies all the requirements for the finite field. So thus we can refer this scheme as GF of 2 raised to power 3. So for convenience, we show that 3-bit assignment used for each element of G of f 2 raised to power 3. So if you take the arithmetic of addition table, and you can take any two numbers from row or column. For example, in the simplest case, we take 6 plus 4. So 6 will be 110 and 4 will be 100. So using the GF values GF 2 raised to the power 3, in which each value uses 3 bits. So it spans the decimal range from 0 to 7. So addition takes place on these 3 bits binary values using the bitwise exclusive OR operation. For example, if we use 110 for 6 and 100 for 4, we get the value 0, 1, 0. That is 0 plus 0, 0, 1 plus 0, 1, and 1 plus 1 again 0, and 1 will be discarded. So which is equal to 2. So here is our additive inverse for each number. So similarly, for the multiplication, you can pick any two values. But in the multiplication case, values in the GF form 2 raised to the power 3 cubes takes place with the modulo of 2 addition, and the result is computed with the modulo polynomial expression. So in this case, polynomial expression is used as x cubed plus x plus 1. So for example, if we take any two numbers such as 3 cross 4, and we take the binary values of these, that is all will be equal to 3 is equal to 0, 1, 1, and 4 is equal to 1, 0, 0. That results in 1100. So the resultant value with the modulo 2 addition is equal to 111, and you take the mod with the polynomial p of x, and in this case we have a p of x is equal to x cubed plus x squared is 0, and then we have x plus 1. So that results in 1 for x cubed, 0 for x squared, 1 for x, and 1 for the final value. So this results in the value 7. So if we take the value 3 from here and 4 from here, we get the value 7. So it would seem that an algorithm that maps the integers unevenly onto themselves might be cryptographically weaker than the one provides a uniform mapping, like the one discussed in the last slide. That is, cryptographic technique might be able to exploit the fact that some integers occur more frequently and some less frequently in the ciphertext. So thus the finite fields of the form GF 2 raised to the power n are an attractive alternate for cryptographic algorithms. So we are looking at the set of consisting of 2 raised to the power n elements together with the definition of addition and multiplication over the set that define a field. We can assign a unique integer in the range from 0 through 2 raised to the power n minus 1 to each element of the set. Keep in mind that we will not use the modular arithmetic, as we have seen in this does not result in a field. Instead, we will show how polynomial arithmetic provides a means for constructing the desired field. So again, consider the set S of all polynomials of degree n minus 1 or less over the field Zp. So each polynomial is again defined as summation n from I from 1 to n minus 1, and we have a x. So there are total of p raised to power n different polynomials in the S. So for the case if we have p is equal to 3 and n is equal to 2, the total polynomial will be 3 raised to power 2, that is equal to 9. And those polynomials will be referred as 0, 1, 2, x, x plus 1, x plus 2, 2x, 2x plus 1, 2x plus 2. So if you increase the value of n, you increase the value of the degree of polynomial. So for the other case, if we have p is equal to 2 and n is equal to 3, there are total 2 raised to power 3 polynomials, and the 8 polynomials will be referred as 0, 1, x, x plus 1, x plus 2, x squared plus 1, x squared plus x squared plus x plus 1. So again in this case the additive table is very simple. You have a diagonal form that each equation cancels the other equation in the opposite direction, and similarly for the multiplication like used in the last example, you must have to define equation p of x to take modulus from. So again values are in GF 2 raised to power 3, and each value is 3 bits spanning the decimal range from 0 to 7. Multiplication takes place on 3 binary values with the modulo 2 addition, and the result is computed with the modulo p of x, that must be an polynomial equation. Additionally, you can use extended Euclidean algorithm to find out the multiplicative inverse. So just like the Euclidean algorithm can be adapted to find the greatest common divisor of two polynomials, the extended Euclidean algorithm can be adapted to find the multiplicative inverse of a polynomial. Specifically, the algorithm will find the multiplicative inverse of b of x modulo a of x if the degree of b of x is less than the degree of a of x, and the greatest common divisor of both polynomials a of x and b of x is equal to 1. So if a of x is a reducible polynomial, then it has no factor other than itself or the 1, so that the GCD of a of x and b of x is equal to 1. The algorithm can be factorized in the same way as we did in the extended Euclidean algorithm for integers. Given the polynomials a of x and b of x with the degree of a of x greater than the degree of b of x, we wish to solve the following equation with the value of p of x, w of x, and the d of x, where d of x is equal to greatest common divisor of a of x and b of x. So we have equation a of x, b of x plus d of x, w of x. So it is very similar to the equation used in the lecture number 5. We had the value ax plus by is equal to our divisor d. So in this case it will be equal to d of x. So in this case we have polynomials rather than the integers. So polynomial is referred as a of x and b of x. So if d of x is equal to 1, then w of x is the multiplicative inverse of b of x modulo a of x. So as we write it here, so if d of x is equal to 1, so wx is the multiplicative inverse of b of x mod, so w of x is equal to 1, so w of x is equal to 1, so w of x is equal to 1 mod, so w of x is equal to 1, so w of x is equal to 1, so w of x is equal to 1, mod, so w of x is equal to 1, 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 so w of a of x. So calculations are similar to the lecture number 5. You can view the lecture number 5 or the table with the extended Euclidean algorithm to perform the arithmetic operations. So there are some computational considerations. A polynomial of f of x in the form g of f 2 raised to power n is similar to the other polynomials represented earlier, I from 1 to n minus 1 a of I x raised to power I. So it can be uniquely represented by the sequence of its n binary coefficient. For example, if we represent this number, we are representing a polynomial with the highest degree of 2. That means x square plus x plus 1. So thus every polynomial in this form can be represented by n bit number. So in this case, if we have n is equal to 3, so every possible combination in the form of gf2 raised to power n can be represented using n bits, in this case 3 bits. So addition becomes the XOR of these bit strings. We have seen that the addition of polynomial is performed by adding corresponding coefficients, and the case of polynomials over Z2, addition is just the XOR operation. So addition of two polynomials in the GF2 raised to power n correspond to the bitwise XOR operation. Multiplication is shift and XOR. That means if you look at the last example, we made one point shift and then perform the multiplication with the another polynomial defined for table. So it is referred as longhand multiplication. So there is no simple XOR operation that will accomplish the multiplication of g of f to raised to power n. However, a reasonably straightforward and easily implemented technique is available. So this technique is referred to the d of f 2 raised to power 8 using an equation in the form of m of x that is equal to x raised to power 8 plus x raised to power 4 plus x raised to power 3 plus x plus 1, which is a finite field used in advanced encryption standard. So the technique readily generalizes to any equation form of g of f 2 raised to power n. So the technique based on the observation that x8 mod m of x. So this results in the simpler form of equation that is equal to x raised to power 4 x raised to power 3 plus x plus 1. So if we follow the multiplication by x, that can be implemented as a 1-bit left shift followed by conditional bitwise XOR. So if you multiply x with the equation f of x, and if the bit 7 is 0, all the bits are considered except the bit 7, and the 0 is added on the left, so rightmost or least significant bit. So if the bit 7th bit is 1, then you use that polynomial and perform the exclusive or bitwise exclusive OR with the value of x. So an equivalent technique for defining the finite field in the form of gf2 raised to power n using same irreducible polynomial is sometimes more convenient. So, to begin with, we need two definitions. Number one is a generator. A generator G of a finite field f of order q contains q elements in an element whose first q minus 1 powers generate all the non-zero elements of f. So the elements f will be considered 0, g raised to power 1, 2, etc. up to g raised to power q minus 2. So you can consider a field of f defined by the polynomial f of x. So an element b contained in f is called a root of the polynomial of f of x if f of b is equal to 0. Finally, it can be shown that the root of g of an irreducible polynomial is a generator of finite field defined on that polynomial. So let us consider the finite field g of f 2 raised to power 3 defined over the irreducible polynomial x cubed plus x plus 1. Thus the generator g must satisfy f of g is equal to g cubed plus g plus 1. That must be equal to 0. So you should keep in mind that, as discussed previously, that you do not need to find the numerical solution for this equality. Rather, deal only with the polynomial arithmetic, in which the arithmetic of the coefficient is performed modulo 2. Therefore, the solution of preceding equality g cube is equal to g plus 1. So we can show that the g is in fact generate all the polynomials of degree less than 3. So we have following. For example, if we have g for 0, we have 0, and we have boundary representation of 0. So if we take the next value, we have g raised to power q. In this case, q is equal to 1. This represents the polynomial representation of 1, and it is represented in the binary value 1 and hexa 1. Take the power to 1 further, g raised to power 1, g 0 1 0 2, g square, and g cube that we specified is equal to g plus 1. So which is 0 1 1 3. G4 is equal to g square plus g. Similarly, g5 is equal to g square plus g plus 1. Again, g6 is equal to g3 but with the square. So g square plus 1. So again, g f of 2 cube arithmetic using generator of the polynomial x cube plus x plus 1 is shown, and the addition table is very simple to understand. Again, you have a diagonal flow which represents the additive inverse of each value. Each value cancels each other, and in multiplication you have similar kind of table represented in previous slides. However, in this case the flow is inverted diagonally. So in this lecture we discussed the polynomial arithmetic, mainly ordinary polynomial arithmetic and the polynomial arithmetic with the coefficient of in the z of p. So we also seen a finite field of g of f 2 raised to power n, and we identified the modular polynomial arithmetic in it, and we presented a way to find out the multiplicative inverse. If you want to study more, you can read the chapter 5. If you have any question, you can ask me through designated channels, or you can conduct a question and answer session. Thank you very much.